and welcome to week 3 workshop for CIV 4SD3 structure analysis and design tree. In lectures we have taken the theory and one example about the singly reinforced concrete beam, the design of singly reinforced concrete beam, and on my lectures I finished most of the main examples, but I just like to discuss more about how we do a couple of checks that is required for the standards. So for examples, let me go back and do that examples, open it again. Let me share the screen as well, so I can demonstrate that one. So I think we find this MUO. Based on that MUO, we need to do a couple of checks. Meaning that we make sure that this MUO, which is MUO 327 kilonewton per meter, is adequate. Adequate means, let's say I have this beam with the UDL load. And if I have this beam with the UDL load, and if I have these cross sections, let's say this is cross sections AA, so that's cross section AA, and I have these 3N. So if I have a certain kind of UDL load, and if you just do the bending moment diagram, see this bending moment diagrams, you will get the maximum moment here. Let's say this maximum moment is 400 kilonewton per meter due to this W loading, UDL loading. Now, so if this MUO, which you calculated, which is 327 kilonewton per meter, is great, probably this one should be let's make it 300 kilonewton per meter, is greater than M star, which is 300 kilonewton meter, which M star is coming from your bending moment diagram. In that case, we will say that the section size, what was the section size? The section size was 300 by 600. So the section size that we have it, which is 300 by 600, is adequate. So the section size is adequate, right? If you have MOU less than M star, you might want, then in that case you need to increase your cross section size to increase this capacity, because for the safety reason it's saying that this capacity of your cross section should be more than your bending moment, so that therefore it's a design moment, therefore it is safe, otherwise it will break for that loading conditions. It fails for this loading conditions. Now if I want to, this is the first and most checking that you always do. Now second checkings that I like to show you is the minimum moments requirement. So if you go back to the standard here on clause 8.1.6, you will see minimum strength requirement. They have an equation for minimum strength requirement. There are PE is for total effective pre-stress force, so we are not working with pre-stress, so PE equal to 0. So if you substitute PE equal to 0, you end up with 1.2 Z FCT dot F, right? So that's pretty much you can do the check. I will show you those checks later on, but this MUO minimum would be 1.2 Z FCT dot F, right? And that is your MU that you calculated should be greater than MUO minimum. All right, so that is the first check. Second check you can make it is this one. The second check that you can make it is this one, the minimum reinforcement. So this minimum reinforcement to making sure that you don't have prevent the sudden failure. Let's do this check minimum. You need to do one of these checks. You don't need to do both. So let's say you have AST minimum should be greater than alpha B capital D over small d square FCT dot F dash over FSY BW small d, right? So that's the equation. I can show it to you again here. That equation is coming from clause 8.1.6.1, and this is the equation. So this is the equations that will tell you the minimum reinforcement required in your beam to prevent the sudden failure. Because you might design your beam, you might design the beam without any reinforcement. Standard don't like it, that you might come up with the concrete and you don't put any reinforcement, right? So that is very dangerous. Your design criteria would be satisfied for most of the cases, but your ductility requirement does not satisfy. So to prevent the ductility, Australian standard has given you this value. So alpha b is just a constant 0.2 for rectangular sections. Okay, so we have a rectangular section. So let's say 0.2. Depth of the whole cross section is given to us 600, and small d is 538. So 600 divided by 538, 600 divided by 538 square. Now fct dot f. Now that equation is, you just need to go back to the section number here, probably here you go, on section number 3 on page number 44. You can find fct dot f is equal to 0.6 square root fc dash in clause 3.1.1.3. so 0.6 square root fc dash. Let me go back here. So 0.6 square root, so fct dot f dash is equal to 0.6 square root fc dash, which is 0.6 times square root fc dash. Fc dash would be your 25 megapascals given to you in the questions. So you can put 25 megapascals. If I use the calculators, I would get 0.6 times square root 25, you get 3 megapascals. So you have 3 megapascals over FSY 500 megapascals, which is the steel Rio. BW is actually your B. Okay, that is BW is actually your B, which is B is 300. I can show it to you. 300 is coming from here, and then you have 538 is D. This D is 538. Where this small d coming from? We calculated this small d before, which is 538 here. So we plug all the values and we can find the minimum steel Rio. So if I just use my calculators, let's say 538 square times 0.2 times 3 times 300 times 538 divided by 500. You get 241 millimeter square, right? That is the minimum reinforcement that you must put it, regardless of your design. This is the minimum reinforcement that you needed. Let's check our reinforcement area. I think we calculated reinforcement area somewhere. Yeah, 1356. You remember from Rio tables we calculated this 1356. So actual our is 1356 millimeter square, which is greater than your AST minimum. AST minimum meaning 241 millimeter square. So we are okay, right? So that's the quick checks that I perform for the ductility. So your beam will not going to be suddenly just a snap. Okay. So I think that's the remaining part. That's I take 10 minutes to just recapture the from the lecture notes. Let's do the examples now, because most of the students here now. So let's do the examples. Let's say example number 1. As I mentioned, now we have almost 2 hours and 2 examples. So I will not. I will take you very slowly and give you some insight what is happening, and tell you some concept as well that will helpful for your design. Now let's read together. Let's make it this one bigger so we can read it. What happened here? let's make a view 100% and make this one figure bigger. So to the full size. Okay, that's sounds good. So you have 800 by 400 rectangular reinforced concrete span, 800 simply supported. Okay, that sounds good. Let me put it that details here. So you have first sentence, you have no, my rectangle is not good. How about these tools gonna work? Yeah, that's pretty much works. Okay, so that works. How much was that? 800 by 400. So this distance from here to here is 800 millimeters, and this distance from here to here is 400 millimeters. Right, so that's details are given to that. Second details that we have is simply supported, 800 millimeters. So if I draw the beam, here, which is simply supported, one is pill, another one is roller, we have 800 millimeter span given to us, and this one is uniformly distributed load. Let's put that W star at the moment. So if I take the cross sections, it is 800 millimeters. I think I have photographs I can share with you. I think I generally like to do some real work. So this I think can I copy this one? See, copy here, because I just want to put it here so we can write on it. Oh, that's perfect. All right, so what happened here? This is the beam, and if you imagine, let's put the red one. If you can imagine, this is 800 millimeters, 8,000 millimeters. Okay, just imagine, this is not 8,000, but to just mimic our examples, we have a 8,000 millimeters that is supports given here. And this cross sections, imagine this cross sections here, imagine, please make an assumptions that 800 by 400. So that's one is 800 by 400 this way. Okay, so that's what we done. And imagine that you have these loads going on top of it. So that's what I draw. Okay, so I hope you have a more clear pictures by visualizing this one rather than just. I don't like it this way. Maybe when I was students, when the teachers talking about this on the paper, oh, it's not too much making sense. But with these photographs, I hope it makes more sense how the beam looks like and how these supports and how the loading coming and where the cross section is. So that's what we mentioned now. So that is the first line. I just extract the information from the first line what they talk about here. All right, the beam is required to support the following uniformly distributed service load. So it has given you the dead load and it has given you the live load. Now this is a critical load combinations, that your G, this is your G, which is dead load, and this is your Q. So if you want to find ED, which is basically your W star, is equal to 1.2 G plus 1.5 Q. Now, can anyone, do you remember in our class, we done it many times, this one. This is dead load. Now, actually dead load is given to us 22 kilonewton per meter, and this is live load. We have 24 kilonewton per meter. Well, I would like to do this one, 22 plus 24, which is 6 and 4, 46 kilonewton per meter. But standard is not allowing to do this only addition of these 22 and 24. It's asking you to multiply 20% extra with the dead load and asking you to multiply 50% extra to live load. Do you remember from our class? Why do we multiply those extra factors like 1.2 and 1.5? I'm taking you back all the way back to the semester 2 this time, in week number 2 in steel design. Do you remember our dead load, live load calculations? And then we are in the middle of pandemic, and you have this architecture drawing, and that's a lot of calculations we go on. So any suggestion why we done 1.2 and 1.5? That comes here as well. So I thought you already know that one. Any wording? Why do multiply 1.2 and 1.5? Why not is 1.5 here and just 1.5 here, or 1.2 here, 1.2 here? Why there is some variations? Any answers? Just wants to talk with you while we studying as well. So there is an uncertainty in our loading, like someone might put some repair work during the service life of the structures. So whatever this, what standard saying that whatever your calculations dead load, you multiply 1.2, you put 20% extra. Live load, you put 50% extra, because live load is very uncertain. You might have some party, or you might have some extra users over the service. You might change your home to something else, like a medical center or something. People will come more. Let's say you have a residential house. Some residential house is converted into the medical center. So in medical centers there are a lot of people. So there is a various reasons. So therefore we multiply these factors here. Now, so to calculate these 1.2 and those factors W stars, here you have 1.2G plus 1.5Q is equal to 1.2 times G is, so here you have 1.2, G is 22 kilonewton per meter, plus, so that is coming from here, by the way, and the Q is 24 kilonewton per meter, which is live load. So 1.5 times 24 kilonewton per meter. So if I use the calculators, I would get it. Let me open my solution as well. So I will get it 62.4 kilonewton per meter. So this beam will subjected to the 62.4 kilonewton. So these beams which is you are looking has a UDL load of 62.4 kilonewton per meters, right? Now, next steps, let me tell you that, okay, I want to have a, let's say I want to calculate, I want to draw the bending moment diagrams. Okay, I think you've done the bending moment diagram many times. Bending moment diagram, kilonewton per meter. Now, the bending moment at 4000 millimeters would be maximum. Let me represent it by M star, right? So that's bending moment is represented by M star. We call this M star design moment. Okay, this M star we call it design moment. Okay, now you done it many times. M star, which is UDL load, would be W star times L square over 8, right? So let's say let me put this one as an 8 meters, because we have this load in kilonewton per meter. So let's put it in 8 meters. So in this case, W star is 62.4. Let me substitute that, kilonewton per meter times by length 8 meter square over 8. So if I use the calculators, I would get 500 kilonewton per meter, right? So M star is 500 kilonewton per meters. Now, the question is, let me ask you the questions. Now, this beam is subjecting M star value of, let me erase these whole things. So this beam at this particular in the middle has a M star value of 500 kilonewton per meter. Now my question is that my question is, let's say this is 400 and let's say this is 800. Is it 800, right? 400 and 800. Now let's say when I calculate these cross sections here, which is 800, which is which is 400 by 800. Do you remember from my lectures we have examples where we calculate MUO. Let's say my MUO is 400 kilonewton per meter. By the way, this is the capacity of your beam. The name of this one is bending capacity of beam, right? That is the name of ultimate. Let's say U is ultimate bending capacity of the beam. Now, let me ask you the question. Let's assume that is 400 kilonewton per meter. Now, that means that your beam require to carry 500 kilonewton per meter, but the capacity of the beam is 400 kilometer per meter. So does the beam gonna fail, or the size of the beam is adequate or not adequate? Can you answer that one? So I repeat again, your beam that's based on the span and the uniformly distributed live load and dead load, you have bending moment, which is design bending moment 500 kilonewton meters, right? That is you taken from bending moment diagram. And you calculate MUO like lever arm and tension force times lever arms, and you calculate this MUO, which is 400 kilonewton per meter. So my question is this beam size is adequate or not adequate? Because you have MUO, which is 400 kilonewton per meter, which is less than your M star, which is 500 kilonewton per meter. So the beam is adequate or not adequate? You can put it. So in this case, beam is not adequate because you can see that the capacity of the beam is less than the required design capacity. Okay, so that's how we check it. So okay, let's continue our examples. Now, do you remember our magical this one? I think we need to redraw it again here. Now, let me redraw that one. Now, do you remember these magical equations that we need to have a strain first. Strain, where how do you gonna get the strain? There are two strain, concrete strain and steel strain. There are two strain in our beam. Now, what was the ultimate concrete strain? Concrete compression strain was 0.003. Where is given? You can come back to the page 110, and on clause 8.1.3 it says that maximum strain in the extreme compression fiber is taken as 0.003. Yeah, so that is 0.3. What does it mean physically? What does it mean in physically? So if you have this beam which is sitting here, so when I load this beam under this machine, by the way, this will going to push this one down. Okay, so when we load this one, this beam will gonna do this one. Do you agree with me that it will gonna does this? Now when they bend at this particular point, when this come down, the strain at here, the standard saying that strain here you will get 0.003. After this strain, your concrete will start crushing. So what if I draw the stress strain curve of concrete? If I draw the stress strain curve of concrete, after this 0.003, it will start dropping. Okay, your is a maximum strain that it will get. After this one, your beam will going to not increasing any load, it will just come down. Okay, so and that is given in the standard. So this one, steel strain, how do we, let's say yield strain. For example, let me put that diagram here, that you have this steel stress, steel strain, and you have this diagram. So let's say, for examples, if you have this yield strain ESY and you want to calculate this FSY, FSY is given to you. Let's say you have a deform bar, you have 500 megapascals, right? You remember from the yesterday. If you don't remember, I can go back and show you where it is. So if you just few page across, there you go. On table 3.2.1, deform bar class N. Generally, it has a 500 megapascals. We normally use this class N, that is normal ductility, and this is low ductility. And these are the special high ductility steel for earthquake resistance. So this N and E represent the special class of steel that are specifically used for earthquake resistance. New Zealanders are heavily use those earthquake resistance those class, but we normally use for our structures deform bar with 500 megapascals with class N over here. This is 500 megapascal is the yield strength. The young modulus of the steel is given here, close 3.2.2, 200,000. Okay, so if I have this FSY is 500 megapascals, the young modulus of this one given to us is equal to 200,000 megapascals. In that case, if I want to calculate this ESY, so the ESY would be equal to, because this is young modulus is equal to stress over strain, right? Rise over run. So if I substitute young modulus, stress is FSY and this one is ESY, then ESY would be FSY over ES, and FSY was 500 megapascals and E was 200,000 megapascals. So if I just use my calculators, you will get 0.0025 as a yield strength of the steel, right? 500 divided by 200,000, you get 0.0025. So you got this strain, which is yield strain 0.0025, right? So from the strain, you can get the stress, right? How you gonna get the stress? Because for concrete stress, you have alpha 2 FC dash, and for yield strength, you have FSY, that is the concrete and steel. From this stress, you can get the force in the concrete and steel. How you gonna get the force? Once you know the stress, you multiply by area to get the force, which is compression force in concrete, and you will get tension force in steel. And from force, you will get moment, because that is our ultimate goals. We need to find that moment. How do we gonna get the moments? We just multiply by lever arm Z. Multiply by lever arm Z. So that will give you ultimate moment for both cases. Right? I hope you understand the whole pictures. Now let's put these prospects in the let's put these details in our figure. 400 millimeters is given to us. 800 millimeters is given to us. What other details are given from the our examples? It says that FC dash is 32 megapascal, cover is 40, R10 stirrups. Determining the required longitudinal reinforcement. So we don't know the reinforcement here. So we need to find that reinforcement from our examples, that we don't know what is the reinforcement that we have. So that's okay. Now we don't know the reinforcement. That's fine. We will go from there without the reinforcement. Let's say probably we need to make a assumptions N24 reinforcement. So look, we can't work without the reinforcement. Let's make an assumptions that we going to use. We don't know how many reinforcement that we're gonna use. So let's make an bold assumptions saying assume N24 reinforcement. This is just an assumption. Please note, in the beam, normally we use 24 millimeter, 20 millimeter, 24 millimeters of reinforcement. If you use too small, N equal to 10. By the way, I think there is a one nice tables that gonna talk about. Let me find that one from my handbooks. They will talk about what are the reinforcement we use for the beams. Let me check if I can find that details here. Beam means here. If I remember that, so I can show it to you. No, they don't have any details there at the moment. I think that reinforcement, I think there is a Rio tables that you're gonna carry with you. Let me open that Rio tables, so they have a good details there. So if you go on your LMS, hopefully you have all exams, okay? So you can take a print as well. So if you go here, almost somewhere in the middle. Few minutes. Oh, there you go. This is the table. So you have a 10 millimeters to 40 millimeters of bar. So let me take this one. So let's say you have these tables in our Rio tables. Okay, let me make it bigger. In here you can see this is the bar diameter, 10 millimeter, 20 millimeter, 60 millimeter. Someone might say, okay, you said you forced me to do 24. Why not? I can use 10 millimeters. Well, you can use 10 millimeters, but what gonna happens that later on you have these 10 millimeters. If you put so many bars here like this, you make sure that when your builder gonna cast the beam, it has enough room to go the concrete through between the bars, right? If you taking normal aggregate size of 20 millimeters, this is the aggregate size, so those aggregates should pass through this reinforcement, right? Remember these are Rio are like this sitting, right? These are the Rio. So when you put the concrete, these concrete should pass through this space, right? So therefore normally we go for these 24 millimeters for the beams. Okay, so that's the reasons we make these assumptions n equal to 24. So based on this n equal to 24s, if I go back here and then if I have these fitments, what was the fitments? I think yesterday I showed you the fitment stirrup, R10 stirrups. So you have these stirrups. I can show you those stirrups again. This is R10 stirrups. Right? Probably I have that pictures with me. I'm gonna show you that stirrups. So these figures here, you can see this is the this is just typical reinforcement. This is sitting, by the way, in our Bendigo campus. Okay, so here you have, this is the stirrups. I hope you can imagine this is the stirrups. These are the stirrups, right? That is help the shear resistance. So those are the stirrups, and these are our main reinforcement in our example. I'm not sure what is the dia here, but we taking N24 in our case. So that is the Rio. So that is the stirrups that I put it here. Now yesterday I told you that we need to find this d, this small d. This is always we need to find it, small d. Now to find the small d, we need to take, by the way, this cover is 40 millimeters given in our examples, 40 millimeters, and then N24 and this Rio. So let's do the small d equal to 800 millimeters, which is capital D. Take away these cover 40 millimeters. Take away this stirrup 10 millimeters. Take away this 24, divide by 2 millimeters. So if you use the calculators, you might get this small d as a 738 millimeters. If I put this one in the equation, d, take away cover, take away stirrup dia, take away Rio dia, divide by 2, right? So that's small d. Now we're going to follow this philosophy here: strain, stress, force, moment, SSFM. Okay, that's what we're going to follow. So for SSFM, which is the stress, let me put there some reference line there, so we have some guide there. Now for that case, let me draw this vertical line here. For that vertical line we have concrete strain. Let's say this is 0.003. Where is this coming from? I show you that 0.03 strain in the concrete. Let's say this is the tensile strains in the steel, and this is the neutral axis. So that is strain profile. Now after strain profiles, if you remember the stress profiles, let me draw this blue line again. And then you have a neutral axis. Let's say draw this neutral axis. Now our stress profile for compressions, it will not gonna touch the neutral axis, but it will just go little bit high, little bit above the neutral axis. Okay. And for this 0.03, we have a stress in the concrete alpha 2 FC dash. Someone might say that, oh, example has given you alpha C dash equal to 32 megapascals. Why not you using straight away concrete compression strain 32 megapascals? Why you multiplying by alpha 2? The reason for that is that we explain you that one, that if you draw the concrete compression strain, let's say this is concrete stress, concrete strain, and if you draw it, it's like this. And if someone asks you to find the area under these stress strain curves, you will have a hard time, right? Engineers don't like it. Now, if someone say that, how about if I tell you that this area that you said it, that can be represented by this rectangle. How about that area, that let's say this area is a concrete of stress strain curve. That area here that you're going to put it in the square would be almost equal to this AC concrete stress strain curve. I'm very happy here because just area of this one. So standard say that that's okay. You have this alpha 2. Right, so this alpha 2 here, this is FC dash, which is 32 megapascal in our, because this is maximum concrete compressive strength. You get it. After this, it will try to go down. So standard say that's okay. I will going to replace this one by something like that here. So in that case, your FC dash become alpha 2 FC dash. That become alpha 2 FC dash, and this line from here to here, which you got it, that will be go like gamma dn. Okay, so they said gamma dn. So if you use these two parameters, you will going to get this this gamma dn and alpha 2. So therefore we just reduce this alpha 2 FC dash. This just simplify version. So you have this compression stress going from left to right, and the height of this one would be gamma dn. By the way, dn is this one, depth of the neutral axis. And then you will have this tension force. Let's put the green color in tensile stress, which is, let's say, sigma st. Okay, and let's put this sigma c concrete compression force. Let's put the red colors there. Sigma cc. Concrete compression force, concrete tensile force going left to right. Now, after the stress, what was that force? SSFM. So strain, stress, SSFM. The next one was force. So let me draw up the force here. Now, on that case, force, you would have this force going in the center. Let's say concrete force, and that centers would be false here, which is gamma dn divided by 2, because it will act in the centroid, and you will have this tension force. Let's say tension force of the steel will act at the center as well, and that will represent your lever arm Z. Okay, And if you want to calculate the moments, MUO. Okay, that is the ultimate moment of this cross section. So that's how we going to work it out. So now let's do this one. So our ultimate goal is to find this AST. How are we going to find the AST? First of all, we're going to find the concrete compression force and tensile force, and we're going to do the equilibrium, and from that equilibrium we're going to find the dn value, and from that dn we're going to find the AST. So of course always we need to find this dn. Once you solve this dn, your most of the calculations would be simple. The most primary challenge is to find a dn value, okay, depth of the neutral axis. Now depth of the neutral axis would be governed by two ways. That if you know your area of the stills, so always we need to find this dn, right? There is always challenge. If you know the dn, then others would be very simple, because dn will govern many things, because depth of the neutral axis we don't know. That's the initial one. So if you want to find a dn, and if the AST is given, somehow standard question saying that you have a 3 and 24 bar and so on, you can just use the equilibrium C equal to 2, you can find Tn. But if AST is not given, in that case you have M star given, and from M star you can find the Dn. I will show you how you're going to find the Dn value for this M star. So let's start putting together all the details. Let's say concrete compression force. We found the strain. So strain is not an issue for us, because we have 0.03 and EST. We need to find this stress and force. So let's calculate the concrete stress first. Let's calculate the concrete stress. So let's say concrete stress is equal to alpha 2 FC dash. Now in that case, alpha 2 equal to, go to the standard. This is the alpha 2. Alpha 2 here, close 8.1.3, and alpha 2 equation is 0.85, take away 0.015 FC dash, alpha 2 greater than equal to 67. So let me write it down. That 0.85 take away 0.0015 FC dash. Now yesterday student asked me good questions there, that what is the unit of alpha 2, right? Because this is megapascals. So if you have megapascals, you can get this one megapascals as well, right? But this is an empirical equations. They don't have any units. This is just a constants. How they done it? They done a lot of experiments. They done some experiments. Let's say this is 20 megapascal, 30 megapascal, 40 megapascals, and let's say this is alpha 2. They conduct a lot of experiment, and they do curve fitting, like equation fitting, and they find these equations by the curve fitting. So they don't have, this is empirical equations, they don't have units. Okay, so that's the quick explanation for that. 0.85, 0.015 FC dash was given in our examples. FC dash was 32 megapascals. So 32 megapascals. If you solve this one, you will get 0.802, and quick check that is always should be greater than 0.67, right? So therefore it is okay, the right part. Every 15 minutes let me pause and just take a breath, and then we move forward. All right, so we have alpha 2, which is 0.802 times by 32 megapascals, which will give me 0.802 times 32, which is 25.664 megapascal. So this is the stress in our concrete. Now if I want to find the force in the concrete force, so you will have, let's say, stress of concrete, let's say concrete stress times the area of the concrete. area of the concrete. Now the concrete stress, we will have 25.664 megapascals. Generally megapascals, we can write Newton per millimeter square. 1 megapascals is equal to 1 Newton per millimeter square. Now area of the concrete. Now yesterday I did not look. Yesterday I tell you, but I think it was even I don't feel that I explained you very nicely there. So I want to use these pictures here to explain you how the area was. So everyone with me on these pictures. Let me make it a little bit bigger. So everyone with me in these pictures. Now so far that we use this one. Let's say you have this Rio here and you have these stirrups here and so on. Okay. Now, so you can imagine that one. Now here we know this is alpha to FC dash. Oops, sorry. Let me put this. We have this alpha to FC dash. This is a stress in the concrete at here. Okay. Now, now we have this area. Let's say this is a neutral axis somewhere here. We don't know. That is dn. We don't know. That we are trying to calculate. And for that one, we have some kind of this one, right? Because you remember that alpha to FC dash, and this is your gamma dn, right? So if I want to calculate the force, if I want to calculate the force, which is stress times by area. Stress, of course, alpha to FC dash. Now the area would be gamma dn. I hope you understand that. Gamma dn times by this b. This b. I hope you understand the cross section area that I am talking about. That if you have this stress, then area would be gamma then b, right? You understand that? So hopefully that make more sense with the pictures, that you have this this cross section area where you have b and you have gamma dn. So I hope it is visualizing, because with the pen and papers it may not be able to visualize more, but here you can see stress alpha to FC dash, which is on top, but for that stress times by this area. The stress are generally going to distribute over this, let's say consider as a pressure. Okay, so you have stress, and if you want to find that force acting on here, so this stress times by area. Okay, I hope it is makes sense. Let me go back to that view. So everyone understand now that area would be gamma dn times by b, right? Now let me go back and substitute all the required values there. That we have 25.664 times by gamma. I think gamma we need to find. Gamma equal to, I just write it down this equation and I will show you where I have written from. 0.025 FC dash, gamma should be greater than 0.67. So here you have gamma 0.97, take away 0.025 FC dash. So that's substitute that value, 0.97, 0.025 times by 32, you get 0.89, and which is greater than 0.67, so therefore it's okay. So you have 0.89, we have 0.89, we have dn. D value was 400 millimeters, right? It's given in our examples, the width of your beams. In that case, concrete compression force in terms of 9136, if you use your calculators, you will get 9136.4 dn, right? Let me put it in the, we may use it this one. Let me give them equation number 1. Now after that, let's make another assumptions. I think these assumptions also we need to validate. That assumptions is from yesterday. Remember, steel is yielded. Let's say steel is yielded. So if the steel is yielded, then tension force in the steel would be FSY, stress times area, same thing, AST. So FSY is 500 megapascals and AST we need to calculate. So let's give them, let's put it in the box, we're going to use it. Let's give them equation number 2. Now let's take the moments. Now we found the force. Now let's take the moment. Let's take the moments. So moment, some of the moments, if you want to calculate the moments, if you want to calculate the moment, either c times z or t times z. But basically we need to find a dn first. So this, either you can do this one, right? Because the moment can be calculated. Let's say muo, you can have c times lever arm, or both will give you the same answers, or you will get T times Z, right? Compression force times lever arm, or you can take tension force times lever arm. Now, we look in these equations, T, we don't have dn. Our first intention is to calculate dn. So we should be good in our hand if you calculate this C, because it has a dn. So that's good. So we can use these equations rather than this one. Now, lever arm Z, we can calculate this lever arm Z. Let me show you this lever arm Z. Lever arm Z would be this D. From here to here is D. So this D, take away gamma dn divided by 2, will give you the lever arm. So small d, take away gamma dn divided by 2. Small d, I think we calculated 738. Take away gamma. So I think small d we calculated. I can show you where it is. There you go, 738 millimeters. Gamma we calculated was 0.89. So 0.89 times dn divided by 2. Right? So that is the our gamma values. Now let's simplify that. 738 take away 0.89 divided by 2, you get 0.445 dn. Now let's substitute this value here. Section capacity equal to compression force, that is equation number 1. Where is it? I think we put it in the there you go, 9136.4 dn. 9136.4 dn, that is compression force of concrete times by the lever arm 738 take away 0.445 dn. Right? Now this is an equations. Now we need to calculate this MOU. Now this is a requirement. The capacity of your beam should be greater than equal to m star. I tell you at the start of our workshop saying that the capacity of your beam, this is a strength requirement. The strength requirement saying that whatever the capacity of your beam should be greater than this design moment, that design moment coming from bending moment. Now this greater than signs we can also make it as equal to for simplifying our mathematics. And this is a capacity reduction factors. And that capacity reduction factor coming from table 2.2.2. So if you go back to table 2.2.2 here, we're going to use these tables many times. So you will not gonna miss any. Table 2.2.2, capacity reduction factor 5. And we going to do with bending without axial tension and compression, that is the section number B. And for member with class N reinforcement and tendon, so we are using for here we are just using the 0.85 at the moment. So someone might say why not 0.65 and so, but I think we just use the 0.85. I will tell you how the 0.85 will count, because there is a compression control, tension control, and tension controls. As you know, we are doing the singly reinforced, and we will going to check these assumptions that we have 0.85 saying that our steel are yielded. So this is attached with our assumptions with the steel yielding, right? So if that assumption is valid, then is 0.85 we can take it. Okay, so that is 0.85 times MUO is equal to M star. M star, do you remember? We get it from the bending moment diagram. That M star would be given to us 62.4, right? Oh, sorry, M star was 500 kilonewton meters. So 500. So you have 500. So MUO equal to 500 over 0.85. We will get 588 kilonewton meters. I like to work it into newtons and again in millimeters. So you have Newton millimeters. So I multiply 2 times. So 588 times 10 raised to 6 Newton millimeters. Right. So this is MUO now, which is 588 times 10 raised to 6. We substitute this value here. Let's substitute that. 588 times 10 raised to 6 Newton millimeter equal to, let's copy this, 9136.4 dn bracket 738 take away 0.445 dn. And now this is quadratic equations. For these quadratic equations we need to solve these quadratic equations using so you know this quadratic equation, 10 raised to 6 Newton millimeter. If you expand this bracket, you might get it 9136.4 times by 738. You get 6742.663.2 dn. Take away 9136.4 times by 0.445. You get 4065.698 dn square. Right. So if I just make it on the one side, 4065.698 dn square, and then minus 6742663.2 dn plus 588 times 10 raised to 6 Newton millimeters equal to 0. And then 6742, I'm just checking the solution, so that's all good. Now if you remember this one, ax square plus bx plus c equal to 0. So a equal to this one, b equal to this value, and c equal to this value. So if you want to calculate this dn, you could substitute minus b plus or minus b square minus 4ac on 2a, right? So if you have b value, you can substitute this b square, you have take away 4, you substitute a, and then you substitute this c, and over 2a this one. So if you just substitute that, you will get dn equal to 92.33 millimeters. Right. Once you find the dn, that is very good news, right? Once you find the dn, it's our, if I have times, I will go back and explain you this minus b plus or minus b square minus, but it's, I think you done this quadratic equation many times. I think in grade 8 and 9, you can do it in your own time. So once you find the dn, it's a happy time start for us, because that will solve a lot of problems. So if you solve dn, then concrete compression force will be solved, because if you go back and check these equations, 9136.4 concrete compression force, 9136.4 dn, equation number 1. Then you said 9136.4 times 92.33, then you will get 843 563.8 newtons. It means that you will have 844 kilonewtons. Just divide by 1000. So that is the compression force in the concrete. That's we found. Now we need to calculate AST. So as you know, equilibrium. Compression force in the concrete equal to tension force in the steel. Compression force in the concrete is 844 equal to tension force Tension force we have in the steel, equation number 2, 500 AST. So 500 AST, right? So if I just convert this one into, let me put this Newton one first, rather than this small number, 843 563.8 Newton, because that is in the Newton per millimeter square, megapascal. So we want to keep it Newton as well. Now, so if I want to find the area, AST 843 563.8 Newton over 500 Newton per millimeter square. So in that case, you will get AST of 1687 millimeter square. What does AST means? This AST means whatever the tensile reinforcement that you require to achieve these moments. So if you put 16807 millimeter square area and more, you will be able to achieve m star value or more. Okay, so that is good. AST we found, longitudinal reinforcement. Now we make an assumption n equal to 24. You remember that, right? You remember assumptions that we make it in 24s. There you go. Assume n24 reinforcement. Now for this n24 reinforcement, can I copy this one? We can drag it, but not copy. Okay, so that's fine. So n24, and we have an area of 1687. So let me copy these tables which we have it in here. Yes, here you go, copy, and then you will just going to get it, let's say here. Okay, so here you go. Let me help you out to explain that. Now help me out here. Now we have n24, right? So we can just, we have n24, we can just go down here. Now how are we going to go down? We need to find 1687. 428 millimeter square area, no, you can't use that. 902, we can't use it because it's smaller than 1687. We can't use this one. That sounds good. 1808. And if you go across 1808, you can find number of bar 4. So I would say that we can take 4 and 24 bar because it has area of 1808 millimeter square, which is greater than our requirement of 1687 millimeter square. So your final answer saying that AST is 1808 millimeter square with 4 and 24 bars. Right? I hope it makes sense. Yeah, you can unmute yourself and tell me if you're struggling to find these informations not flowing through. Is it all good? So there is a second question as well, saying that, okay, you done all these long calculations. How about you solve using the quadratic equations? There is a ready quadratic equation that we can use it. They said first principles we finish by solving quadratic equations. Okay, someone might ask where these quadratic equations coming from and where is in the standard. Look, this is not given in the standard. There is some theory. We can prove it. How are we going to get this quadratic equation? I have very small videos on this how to prove it. This one. So if you want, you can watch it, that small video there. I can point it out later on if I have time. But is this quadratic equation which I am writing it? That's basically is equilibrium and all which we saw. That is just a condensed version of this one. Okay, so this is a quadratic equation, and they said please find this AST using these quadratic equations. If you like, you can put it in your cheat sheet. These equations, it's very helpful equation, is quick and straightforward. So basically we have to find this AST value from this quadratic equations. Now MUO, we calculated that. MUO we calculated MUO we calculated. Where was that? MUO we calculated M star, I think somewhere here. We calculated MUO, I think 588 times 10 raised to 6. So that's, we can use that ready equations. 588 10 raised to 6. AST we need to find 500. I think the D value that we already know is 738. 1 take away 0.5. Alpha 2 we calculated 0.802. FSY 500. FC dash 32. AST we need to find. B was 400 and D was 738. Okay, all the parameters that we done in the A, that we can use it. So if you have 588 times 10 raised to 6, and if you just expand this one, like multiply this by 1 here, you will get AST times 36900. Take away, you again multiply this whole chunk with this big number here, you will get AST square times by 12.18. So if you just put these equations in a format, let's say 12.18 AST square minus 369,000 AST plus 588 times 10 raised to 6 equal to 0. Again, this is quadratic equations. A x square plus bx plus c equal to 0. If you want to calculate c in the x, in this case AST, can have minus b plus or minus b square minus 4ac over 2a, and you can find AST equal to 1517.5 millimeters square. Someone might argue, okay, that looks a little bit different. Yes, of course it's a little bit different because it has a lot of rounding off and all. So we get this one 1687, we get here 1517. Still we're going to use these tables. We can't use this, we can't use this, we can't use this, we can use this one. Still our answers will be standing same, that we're going to provide 4 and 24 bar with AST value of 1808 millimeters square. Right? So any questions for this one? I know it is long, but I think we take a time to solve this one. But let me stop here talking about section B, that what they want is this locate where along the span halfway to logarithm can theoretically be terminated. Okay, look, what they say that, okay, if you have 500 kilonewton meters, if you have 250 kilonewton per meter, where you gonna terminate it? You need to find the x distance. Now look, I need to make you this explain this. Mathematics is very simple, there is nothing, but I want to explain you this in the theory, what is happening actually. So I come across, I have written some notes here to explain you. I will go through with you this one, and it's because if I write these details, it will take long time and we may not be finished. I will encourage this. There is a lecturer here in Curtin University. He put the YouTube video for detailing of reinforcement. Very helpful, and I took these notes from him. So I like to acknowledge him for his contribution and explaining this in a very simple format. So we call it curtailment of flexure reinforcement. What is curtailment? Curtailment is the reinforcement is cutting off some of the reinforcement bar in the tension or compression where they are no longer needed for strength purpose. What I say that, look guys, you have M equal to 500 kilonewton meters, and you providing this reinforcement at 1808 millimeters square. but that's 1808 millimeters square. That is for 500 kilonewton meters. What about the moment here? That is very small compared to 500. So why do you need the same amount of reinforcement going across here? If I explain it in the figures, because this will be more easier. So it says that okay, you have 500 kilonewton meters reinforcement, 500 kilonewtons here, and you calculate the reinforcement here. That is going along here, 4 bars, 3 and 4, and this is 4 and 24 bar. That's good because you have this 500 kilonewton meter, which is good. Now it says that, but the bending moment here in this region, around this region here, is very small. Why do you need this extra bar going here? Right? You can cut it off. This is a curtailment. Why do you need the majority of the bar here, not in this region, because your bending moment is very small. So it says that you can cut it off. Curtailment. Standard has a one clause. Probably later on I will show you that one. So this curtailment saying that if you have let's say this is bending moment and you have 4 and 20 bars, basically this is the moments here, right? You have this maximum moment m star, this is the moment here m star. Then if you come halfway through, like a halfway moment, then why do you need, what you need to know it that okay, this is a reinforcement, right? Actual reinforcement here going. So in that case you have 4 bars. Of course you need 4 bars here. Of course you need 4 bars here because you calculated 4 bar in the moment, but you may not need the 4 bar here. You may need the 2 bars here. But how you going to cut it off? Saying that okay, you have here, of course you need 4 bars. Then you can find that distance here and you can cut it off, right? So this is a theoretically cut off points. Okay, theoretically you can cut off here. You don't need this bar, but for practical cutoff, we need this what we call this one development length. Later on, I will explain you. I think in week 6 or somewhere we have development length. So you need the development length to create the bond between the concrete and steel. So it's actually you need to extend this bar up to this point, which is practical. But in our question, is asking you this point. But actually in real world you need to have some extra things as well. So basically what is explained, what is this telling you? I hope it makes sense. I'm not over making complicated for you. I hope it is makes sense. So what is saying that, look guys, if you have this bar going, 4 bar going here, you can have these bending moments. Let's say I draw the bending moments here, respective bending moments here, and this is 500 kilonewton meters. Now it says that okay, look guys, you have only here 250 kilonewton meters. So why do you need all these bar here, right? So you can cut it off. So just you can have curtailment. So you can have only 2 bars here. Probably you can have only 2 bars here rather than 4 bars. So we can cut it off. But actually you need to extend a little bit. LST, that is the development length. So that LST we're going to find it later on. So that's what they're talking about here in the question. I hope you're gonna make sense. So it says that locate where along the span 1/2 of the longitude can theoretically be terminated. So that's not complicated. Let me walk you through with the examples there. It's not complicated to do it. So what it says that this is second examples. Oh, okay. So he says that you need 50% of the MUO, right? Because as I mentioned, you have MUO of 588. So you just need to divide by 2. So 294 kilonewton meters, that is the halfway through. So basically, if you just do this reaction force, and if you just find the reaction force, you know the structure analysis, mechanics of solid, and then you just cut it off your 294 kilonewton meters, that is you here, but you need to find this x distance where it gonna locate these 294 kilonewton meters. So in that case, you just have a 250 times x, that is the moment, equal to 294. So x equal to 1.17 meters. So basically it says that from here to here you have 1.17 meters, where you don't need you don't need the additional reinforcement. Okay, so that's what it's. I explained you that one in the picture as well. So it says that it's basically the bending moment diagram playing with that one. So basically it says that if you have 8 meters of, where is my figure? Basically it says that if you have a 8 meter of 8 meter of 8 meter of beam, 8 meter of beam here, and then if you just don't need these 1.17 meters, you don't need those 4 bars continuing from there. So we have finished 1 hour and 15 minutes. Probably it will go through these assumptions. Probably you can calculate the 0.025 yield strength, and then what was the actual strain in the steel, and you can validate that assumption. I think I done it in the lectures, and probably you can do this minimum reinforcement check as well, minimum AST requirement as well. Probably I encourage you to do, because we calculate this AST 1808, right? So you need to do this one. Probably I show you at the start of the lecture that you can do this one, that AST, you can calculate AST alpha B, very simple. Alpha B is 0.2, D is a what was 800 and 738. FCT dot F is a 0.6 times square root FC dash, so that is goes somewhere in front of the standards. FCT.F is going somewhere here in close 3.1.3. You have FCT.F, and where was that? Yes, and here FSY 500, BW is your B, I think 400, and small d is your depth 738. So if you have AST minimum, I think this check will go through. So make sure that your AS value A1800 is greater than this AST minimum. It's a check that you can make it. Okay. At the start of these lectures, I explained that one for our. It's a very quick. Max is very easy. Okay. That. Anything else? Any questions there before we moving on to this one? All right, we have around 30 minutes to crack these examples. Let me go through these examples real quick. Probably most of the things are covered. It's exactly the same. Design the longitudinal reinforcement for this one section, so on. M star is given. Everything is given. It's almost identical. There is not basically any difference there. Okay, look at this. All the details. Well, they make your life easy here. They straight away give you M star, right? And FC dash and covers and everything. So probably it would not be. It's exactly the same. Let me take you through this one in 30 minutes. Most of the details we cover. Sorry, we have already in my OneNote. So, but by the way, giving any break. But I hope you are final year students, and I just want you to give you as much more detail as possible. You know what I mean? It's just it's not that I want to. It's not only that I just want to give you the details that you just need for your exams. It's just some of the details that I'm just trying to explain would be helpful in your career as well. So the intention is not only to just take you through just the only those are covered in syllabus, and those others said, okay, my course is not the course is not talking about, don't worry about it. So it's not that intentions. My intention is to just give you, our intention is to just give you more details there. So I think you know the drill now. I think I mean the drill now means you know the styles and procedures what we are talking about. Let me put a little bit wider. So I will talk less now. You can stop me if it is too fast for you, but I think basically everything was covered here. What was the assumptions we want to make it? I think N24 bar again. How about we go N24 bar again? So this is the assumptions. We will take N24 bars. We don't know how many of them. We just randomly put 30 cover, R10 stirrup. So that's good. We have these stirrups, R10, 30 cover. So I think the first step is always small d. which is 1200 depth. So this is 1200. I think you know the drill now. 1200 millimeters, take away this cover, 30 millimeters, take away this stirrup, which is R10. Stop me if it is too fast, okay? Because all these details I take you very slowly there. And this Rio dia is 24 millimeter divided by 2. You get this small d value as a 4. Oh, sorry, that's other way around. I think this cross section is sitting like this. Why is like that? Is the longitudinal reinforcement for 500 by okay, so depth is 500, sorry. So depth is 500 millimeters and width is 1200 millimeters. So we just need to replace this one by 500. So you will get this 400 and 488 millimeters. All right, now you know the drill now. I think the strain, we're gonna take it 0.003 EST, and then we're going to take you through the stress. Basically, let's say this is neutral axis. Basically, this alpha 2 FC dash, and this is gamma dn, and this is steel stress. This is concrete stress, and then you have force going here, concrete force, tension force, lever's arm Z. This distance is gamma dn. Lever arm Z is equal to this d, take away gamma dn divided by 2, and this moments is t times z. So I think I repeat this 5 times, I believe, now in the lectures and these workshops. So I hope you can just try to absorb this information as much as you can. Now M star is given to us. M stars, and you know the drill now, that capacity factor times the section capacity, ultimate section capacity, should be greater than your M star. For maths, we just take it as an equal to, so we can simplify our maths calculations. Now let's say steel is in there and under reinforced and so on. We can just go back to this table again. I think table 2.2.2, table 222. I remember that one from our example. Yeah, table 222, capacity reduction factors. I think I have it in these standards. I have very nicely written here. Okay, so table number 2. So these capacity reduction factors account for uncertainty in material strength, inaccuracy in design equation, approximation in analysis, variation in dimension, variation in placement of reinforcement. So there are many uncertainties, that therefore we reduce this capacity. Now it says that, look, do you remember I was talking about that if you design for over reinforced concrete beam, your design will be penalized by 35% of your, the standard will give you penalty. But we are designing as an under reinforced, not over reinforced. So we are just taking 0.85. This is an assumptions. Of course, you can validate that assumptions with your yield strength is steel strength is greater than yield strength. So we have 0.85 MUO, and that is 300 kilonewton meters. That's 300 kilonewton meters given in our examples. So we just do this MUO equal to 300 kilonewton meter over 0.85. You get 353 kilonewton meters. Now once you get the MUO, we have a quadratic equations. If you remember that quadratic equations, so MUO, let's use the quadratic equations. AST FSY D 1 minus 0.5 alpha 2 times AST. I have a video which is going to explain you how to, it's not important how you, but if you need more knowledge, so you can use this video. Now some student might say, okay, I'm coming to university not to watch the video. Well, I agree with you. I don't encourage you to watch this video, but due to the time constraint, I want to cover the important stuff. So the derivation of this equation is not that critical and important. Therefore, I'm not covering it. Otherwise, I would explain you this one step by step. I'm just giving the priority those things which are useful. So therefore, I encourage you to watch. But after watching, of course, if you have questions, we are available to answer the questions. Okay. So this alpha 2, I think you remember now where this alpha 2 comes from. Section 8. Now go to section 8, and then alpha 2 was here. This one, close 8.1.3. So 0.85, take away 0.015. Fc is given in our example 25. I can show you that is 25. So alpha 2, by using the calculators, you get 0.8125. You remember that it should be greater than 0.67. So that is okay. I think that's the only information that we needed. So we substitute this MUO now, and that's, let's say, keep the unit Newton millimeters. Let's keep it consistent. So 353, we need to make it in the kilonewton millimeters. So 353 times 1000 times 1000, that makes it Newton millimeters, equal to AST we need to find. FSY 500 megapascals, right? Deformed bars. N is a deformed bars. I think you know now where I'm talking about 500 megapascals and where it's sitting in our standard. And we have 448D. I'm just substituting the value, okay? 1 minus 0.5, alpha 2, 0.8125 times by AST we need to find. BD, width of the beam is 1200. Given in our questions, small d is 448 times 500 over FC dash was 25. Okay, now let me take you through these examples because 353, let's say 10 to the power 6, because I think we did not do any quadratic one. Let me experience the quadratic equations with you. So it's just 500 times 448 give you this one. One takeaway, these whole multiplications over AST will give you this 2.29 times 10 raised to minus. You just need to use the calculators. I hope it is okay. So AST. Okay. Now we can expand these brackets. So 353 times 10 raised to 6 is equal to 224000 AST. And then you multiply this number with this number, you get minus 5.128 AST square, because you have AST and AST, you have square. Let's bring this one across. So 5.128 AST square minus 224000 AST plus 353 times 10 raised to 6 equal to 0. Now, you know the story now, ax square plus bx plus c equal to 0, right? And then if you want to write it in that form, that AST as let's say x equal to minus b plus or minus square root b square minus 4ac over 2a. What is my b? B is this. So you have a minus and minus 224000 plus or minus b is minus 224000 square minus 4, a is 5.128, c is 353 times 10. I just plugged the value. I think you done this one in the grade 8 somewhere, but just refreshing, take you back to the schools. 5.128, a is this one. So simplifications give you this 224000 minus minus is plus or minus square root of whole things will give you 207 208 over this one will give you 10.5. 256. I hope it is not fast. I think it's just the maths. And then you just say that AST would be 24000 plus 20708 over 10.256, or you have AST of 224000, take away 208 over 10.256. Oh, sorry. Oh, completely gone. Wait for that to launch here. Quick, fast, so good. All right, so you have plus, one time plus, another time minus there. Simplifications will give you 424 millimeter square, or AST equal to 1637 millimeter square. This one looks like unrealistic number. Look at that, how much millimeter square you will have. You need to have a maybe 100 bars. That is not possible to fit that one. Probably that's not required. Probably that's one the appropriate numbers. Now 1637, I think we have this. Oh, sorry, I need to get the Rio tables again. All right, so Rio tables. Where is it? Oh, I close it. No, here you go. Let's get the Rio tables and edit, copy. I hope it is not fast. Most of the things are we covered, like alpha 2 and so on. You can do the first principle as well if you like. It's a long way, but it's okay. What about this paste? How do we do paste? Oh, let me go and do it here. Let me put it here. Where is my mouse? There you go. So let me make it a little bit bigger so you can see. Now, what is the we assume? I think you remember we assume 24 and 24. That was our assumptions. In that N24, you have 1637 AST. So you check it. This one not works. This one not work. This one not work. Oh, this one what? 1808. So that is okay. Go across. We have 4 bars. So 4 and 24 bars, which has a area of 108 millimeter square, which is greater than our required area of 1637. So our answer would be 4 and 24 bar with AST of 1808 millimeter square. That is the longitudinal reinforcement required to carry this M star value of 300 kilonewton meters, right? Because the concrete alone will not going to carry all the loads. So we need to have to find those values. Now we need to do the couple of checks as well, ductility, minimum fluxure requirement checks, and so on. So let me do all the checks that I skipped in our first example. So let's experience this one slowly. Okay. Now there is a clear spacing requirements as well that you need to provide. So when you design it, you need to provide the what we call the clear spacing. So let me draw the figures here. Okay, let's draw the big figures here. So you know this is 1200 millimeters given in our example. Now we need to place 4 bars. Bar number 1, bar number 2, bar number 3, bar number 4. And we have these stirrups as well. Sorry, it's gonna touch. It should touch here. Oops, sorry. It should touch like this, touching like this. Like this, okay, and then you have these just 10 stirrups. So that is stirrups. Now we need to find the cover is 30. This cover is 30. Both side cover is all the way 30. All are 30. I think 30, right? So that is given in our examples. Now my intention is, look, when you designing it, your builders need to know what is this center to center distance of the bar, right? The clear spacing of the bar. that you need to specify, right? So how you going to find that that values that you need to specify? So how I do it? Okay, let me check how going to be done. 1 2 and that is 3. Okay, and it's touching, so you have a 1 2 and 3, and then you will have a 1200, just thinking. Okay, 200, 210 stirrup and 4 and bar. So probably we need to specify, sorry, again we need to specify from here to here, clear spacing. Okay, we call it clear spacing, probably clear spacing, not the center to sentence. So this is clear spacing. Let's say I write, sorry, CS, clear spacing and clear spacing. So how I do it? Let's watch it. So this 1200 millimeters equal to this 1200 equal to this 30 millimeters plus this 10. You with me, right? 10. Then you have 24. Then you have this clear spacing. Let's put CS. Then you have 24. Then you have clear spacing. Then you have 24. Then you have clear spacing. Then you have 24. If you are smart, you can do it quickly, but just to start with 10 plus 30. I hope you understand that. So if you want to do it quickly, I would say that, okay, you have 230 because on the both sides, so 2 times 30 cover, plus you have these 2 Rios, so 2 times Rio, and then you have these why you have only 3 4 1 2 3 4 4 bars, 4 times 24, and then 3 clear spacing. So if you simplify that, clear spacing would be 341 millimeters. So your builders, you will specify in your drawing saying that you have 341 millimeters of spacings. Now there is a clause that will tell you. I think I will tell you where it is. You need to make a check whether it's the standards allow you to do 841 or not. So clause number 8.6.1b. So just a couple of pages there. 8.6.1b. There you go. Center to center spacing of the bar near the tensor force will not be exceed 300 millimeters. So center to center spacing. Please note this is a center to center spacing of 300 millimeters. So if you want to calculate the center to center spacing, you have this one is 341, and then you just put 12 on both sides plus 24. So that would be 341 plus 24. You get 365. So center to center spacing is 365 millimeters. Now the standard clause 8.6.1b, I was correcting myself. So they say that spacing, oh sorry, yes, I agree with you. So this one should be less than or equal to 300 millimeters. So this is not work. 365 will not work. So in that case, we need to reduce our bar diameters. So let's say we assume N24, we need to take, let's say, N20. So if you go N20 here, and for that we need to make sure this 16337 still satisfy. You keep going, you have 1884, you have 6 bar. So I think that will work. So 6 and 20, and that will have a spacing would be, which would be satisfied. You can calculate again this one using these, and that will satisfy, and our area would be now 1884 1884 millimeters square. So yeah, so standard said you need to have a less than 300 millimeters. You can't, because look, I can tell you the reason for that one. Look, this reinforcement is our soldiers. This reinforcement is our soldiers, right? This reinforcement. Our enemy is the crack. This is a crack, right? Now the standard saying that look, you need to keep this distance, center to center distance, at least 300 millimeters. Okay, not be more than 300. You can't put 400 millimeters or 350 millimeters, saying that okay, if you have a soldiers, you don't want to put your soldiers on the border very far away, then the enemy will gonna go inside. So meaning that this crack will gonna travel if you put your bars very far away. So therefore, to keep this crack control, the standard wants you to keep these 300 millimeters. You can't, if you see for any design that okay, spacing is provided 340 millimeters, is wrong. Standard don't want to allow for any reason for 340. So 300 millimeters is the utmost that you need to provide. Now let's move on. Check the ductility. Now the ductility check has a various options. You can check against with your DN values. So DN, you know how to calculate DN. I think I tell you that in the last example as well, we done this DL. I think it's just the equilibrium of like this, T equal to C. So AST times FSY is equal to alpha 2 FC dash gamma DN B. And if you just make a DN subjects. So in that case, we can have a 1 over alpha 2. Alpha 2 is 0.8125. I believe we calculate alpha 2 at the front. I believe we calculate this alpha 2. And then we can just calculate the gamma. I think we done the gamma value here as well. The gamma would be 0.97, take away 0.0025 FC dash. So you have 0.97, take away 0.025 times by times by 25. Times by 25. So you will get this value as a 0.9075. So 0.9075 FSY 500 over 25 times 1884. You need to use the new one, okay? Don't use the old one with the 6 and death requirement. And you have 1200. So the DN value would be 42.6 millimeters. So we need to get the KU. KU equal to DN over D, and that is 42.6 over 450. You get KU equal to 0.095. Now the standard saying that your KU would be, it's written somewhere here. Let me tell you where it is. Come here. Now is standard saying that KU section with KU greater than 0.36, where this one shall be used only when. So your KU should not be greater than 0.36. That is the magic numbers. Okay. If you are greater than 0.36, that's another requirement. So to satisfy this requirement, you want to have the KU value less than 0.36. If you have greater than 0.36, standard will not gonna like it. So it's a less than 0.36. So therefore it is okay. Okay, the standard will give you penalty if your KU value is greater than 0.36. Now let's check the minimum flux requirement. Minimum flux requirement that is sitting here. I think I explained you at the start. You have this minimum flux requirement, minimum AST requirement. Let's do the minimum flux requirement. Please note PE equal to 0 here. PE equal to 0 because it's a pre-stress force. So you can have this 1.2 Z FCT dot F. So M crack FCT dot F Z. So FCT dot F is 0.6 square root FC dash times the Z is BD square on 6. Where this FCT dot F coming from? probably on section 3. Here you go, fct.f 0.6 close 3.1.3. So if you just substitute that value, 0.6 times 25, B is 1200, D is 500 square. I think we just need to use this 438 D square. Capital D square, let's put capital D square. So 500 square over 6, you will get 150,000,000 Newton millimeters. So you have 150 kilonewton meters. So we need to multiply by 1.2, where it is 1.2 fct.fz. So just 1.2 times 150, you get 180 kilonewton meters. So in our case, we have MUO, which is how much was MUO we calculated? MUO was here you go, MUO was 353. So in that case 353, so 353, which is greater than our minimum 180 kilonewton meters, so therefore it is okay. Our AST has passed all the checks, 6 and 20, has passed the spacing requirement, has passed the ductility requirement. Spacing should be less than 300 millimeters. Ductility is Ku should be less than 0.36. It passed minimum moment. M this O minimum is less than MUO. So it has all the check passed, spacing, ductility, minimum moment. If you want to do the minimum area one, is simple here. You can have AST alpha B D square B fct.f, we calculated FSY, BW is B and D. So you can calculate minimum minimum area. It will pass. So AST that you calculated 18 whatever value should be greater than AST minimum. So I think that's the whole story. Hope you have, but let us know if you have any questions there, or any comments, or anything that does not make sense, or anything I fast forwarded for any reasons, or anything you don't understand. Please unmute and you can ask the questions.